Okay, seems like we are live. Andres, you can go ahead with introduction.
Good. So, hi everyone. Thank you for joining us for yet another Safari Live seminar. Today, it is our pleasure to host Yufeng Gu. Yufeng Gu is a PhD candidate at the University of Michigan, advised by Professor Ritu Parnadas. Before UMich, he obtained a bachelor's degree from Zhejiang University in 2020. His research focuses on computer architecture, hardware-software co-design, near-memory processing, and quality of service optimization. He is developing novel hardware and systems on accelerating large-scale emerging applications such as generative artificial intelligence, Gen AI, and precision health workloads. The title of today's talk is PIM is all you need, a CXL-enabled GPU-free system for large language model inference. So without further ado, let's get started. Yufeng, virtual floor is yours.
Yeah, thanks, Andres, for the kind introduction. Hi, everyone. Today, I will present PIM is all you need, our recent work and the collaboration between University of Michigan, ETH Zurich, and Intel. We open source the artifact evaluation, and feel free to check the GitHub link below. Generative artificial intelligence has reshaped people's lives in various areas, such as text, image, video generation, coding assistance, intelligent agent, and so on. The carbon footprint of the language model is dominated by the inference phase, which is twice as much as training. So the scope of our work focuses on the inference phase. Large language model inference serving is very expensive. The API cost for 1 million output tokens increases with task complexity. The video generation API is currently not available, but its price can be foreseen to be even higher. LLM inference is now deployed on expensive GPU servers. However, the GPU utilization on LLM inference is lower than prior deep learning models. Why is GPU underutilized on LLM inference? So let's first understand how LLM inference works. User sends a prompt, where each token is converted to an embedding vector. These vectors are processed in parallel by GIM operations. After understanding the prompt, in the decoding stage, the model generates output tokens one by one. This autoregressive execution cannot be processed in parallel and takes the majority of the runtime. Here is a LLM inference latency profiling with different length of prefill and decoding phase. For example, with 2048 tokens in the prefill phase and the same length in decoding phase, this table shows the ratio of decoding latency when compared to the end-to-end latency. In this example, we can see with the same length of prefill and decoding tokens, 80% of the latency is corresponding to the decoding phase. And these experiments are profiled at the maximum batch size on the GPUs using the VLM framework. Let's have a deep dive into the decoding stage. To generate one token, the model goes through a series of transformer blocks. Each transformer decoder block is composed of fully connection layer operations, followed by self-attention and then fully connection. The fully connection operates on model weights, while the self-attention operates on KV cache. To serve inference tasks on Llama 70B model, the model weights takes around 140 GB of memory capacity using the BF16 format. With the batch size increasing, we can see the KV cache capacity scales almost linearly. With 4 A100 GPUs, the system can provide 320 GB of memory capacity. At a 4K context length, the memory requirement starts exceeding GPU memory capacity at a batch size of 128. This chart shows that with the context length increasing from 4K context length in the prior slide to 32K context length, the memory requirement increases even faster. This reduces the so for example, at 4K context length, the batch size of 128 requires more memory capacity than what GPU can provide. But at 32K context length, this maximum batch size decreases to 16. This reduced batch size decreases the GPU's utilization. And this chart further extends the context length from 4K to 8K, 16, and 32K. At the meantime, using the green lines to show the throughput. So we can see that the throughput are decreasing. Okay, so sorry, the throughput starts saturating when the batch size starts exceeding the GPU's memory capacity. So the conclusion is with context length increasing, the maximum supported batch size of LLM inference decreases and the GPU utilization decreases. Therefore, the final throughput tokens per second decreases as well. When serving multiple queries concurrently, fully connection operations can be batched because each query shares the same model weights. On the other hand, self-attention operates on user-specific KV cache context, which cannot be batched and has to be processed in a sequential manner. Deep learning models usually apply GEM operations that general matrix multiplication. It has high operational intensity. For example, if we have an input matrix of 4K by 4K dimension and the same dimension of weight matrix, so we can see how many operations there are in this GEM operation. So there are 4K by 4K by 4K by 2 operations in total. This 2 means MAC operation has multiply and accumulation. And it's divided by how many bytes of data we need to fetch from memory. That is the entire size of these 2 matrices. So this operational intensity of GEM operation is 2000 ops per byte. Today, GPUs are well optimized for this kind of GEM operations, and it can provide 156 ops per byte. However, LLM inference operates on narrow GEM operations. It has a skinny input matrix. In this example, the input matrix size is 16 by 4K. With a similar calculation, we can see the operational intensity for this example, the narrow GEM operation is only 16 ops per byte, which is much lower than the operational intensity that A100 GPU can provide. So that also explains why the GPU is underutilized in LLM inference tasks. How can we efficiently serve LLM inference with such a low operational intensity characteristics? The operational intensity is determined by compute throughput and memory bandwidth. Increasing the memory bandwidth can better support this low operational intensity tasks. The advanced GPUs today have been equipped with high bandwidth memory. For example, the HBM can provide 2 terabytes per second of peak memory bandwidth on A100 GPUs. But their bandwidth is still limited. On the other hand, the processing in-memory solution places processing units near DRAM banks, a single GDDR6 PIM device can provide 16 terabyte per second peak memory bandwidth, which is 8 times higher than GPU. However, the PIM solution actually takes extra area by placing the processing unit close to the DRAM bank. So the processing unit will reduce the memory density of the PIM chips. On the other hand, LLM inference requires pretty large memory capacity. In this example, the LLM inference on Llama 17B model at 4K context with batch size of 128 requires 450 GB of capacity. Within this 450 GB of memory capacity, 140 GB is for storing the model weights, while the other are reserved for KV cache. The advanced LLMs has increasing model size and context length. For example, Llama 3 model size increases to 405 billion parameters, and the context increases from 4K to 128K and further to 1 million or 2 million in other models. Now that PIM solution reduces the memory density and LLM inference requires pretty huge memory capacity, how can we fill this gap? Our solution is to use the CXL interconnect, which can provide substantial memory capacity. Each CXL device has 16 PIM chips, which provides 16 GB capacity. By integrating 32 CXL devices, the entire system can provide half a terabyte of capacity. Meanwhile, the CXL protocol can scale to even larger number of devices. In this work, we propose the Sense system. The whole CPU drives 32 PIM devices through a CXL switch. Each device has a CXL controller, GDDR6 PIM chips, and processing near memory accelerators. Each CXL device has 16 PIM chips. Transformer block contains versatile operations. To map the transformer block to the Sense system, let's first understand what operators does the transformer block contain. The PIM module supports vector and element-wise multiplications, which accounts for 99% of the total operators. Supporting the remaining operations on the PIM device can have large area overhead. So in order to execute the full transformer block on the CXL device, we propose a hierarchical PIM-PNM design to support these operators outside the PIM chips. The PNM accelerators have less compute throughput when compared to PIM modules, but provides flexibility for versatile operations, including vector addition, reduction, and exponent. We also apply RISC-V cores to support special functions such as division. So here is the operations of the entire transformer block. This is the decomposed operators for the RMS norm. The orange block shows that these operations are conducted on PNM accelerators, while the blue block shows that these operators are operated on the PIM modules. And the colors with merged blue and orange blocks are decomposed on the 4 extra blocks, showing that, okay, partial of these operators are mapped on PIM and the other parts are mapped on PNM. The PIM module is composed of near-bank MAC reduction, and the PNM accelerators are shown in the right figure. The fundamental difference between these two architectures is that PIM module locates within the DRAM chip and uses the DRAM manufacture process, while PNM accelerators are placed outside the DRAM chips using the logic manufacturer process. If we look at PNM units in detail, we can see each of the four, so not the four components, but the three accelerators apart from the RISC-V core. These three accelerators all have 32 lanes. They're matching to the 32 channels. That means one lane operates on the data locating on each of the PIM channel. There are 2 channels per GDDR6 PIM chip. In each of the PNM lane, there are 16 operators executing in parallel. So each of the operator operates on the BF16 format of data. It aggregates to 256 bits of data access. This matches the shared buffer data width. Here is the instruction set architecture supported for the nearbank PUs as well as that for the PNM units. In the CXL device, the instructions are fetched from the instruction buffer and proceed to the decoder. PIM instructions are directed into the GDDR6 PIM chips, while other compute instructions are directed into the PNM accelerators, using the instructions that I showed in the prior slide's IC table. Meanwhile, the intra-device communication is conducted through the shared buffer, while the inter-device communication leverages the CXL port. In the next slide, I will explain the data movement, that is a communication IC. So firstly, the data need to be moved between 2 CXL devices through the send, receive, and broadcast or multicast instructions. And data can also be moved between the shared buffer and DRAM banks through the write single bank, read single bank, or write all banks. Also, the global buffer within each DRAM channel can communicate between with the DRAM banks, while the shared buffer can also write bias or load result, MAC result from the processing, the nearbank processing units. Also, the shared buffer can communicate with the global buffer as well to write the input vectors into the global buffer. In order to conduct the inter-device communication through the CXL protocol, the CXL port actually conducts this functionality. Let's see how the CXL port read or write data. Firstly, if the host want to read data from the PIM device, it first initialize a host to local request. And the local PIM device will give response of local to host data response. That means this response includes the data requested from the host. If the host wants to write data to the PIM device, it initializes a host to local request with data, because this write request includes the data to be written into the DRAM banks. After writing the data, the local PIM device will give a response. Because this is a write request, so the PIM device don't need to give any data back, so that is a no data response. The local PIM device can send data to a remote PIM device. That is the inter-device communication supported by the CXL 3.0 protocol. In this case, the local device initializes the request of local to remote request with data, because it's a send request, including the data. After the remote PIM device receives the data and write to the specific address in the shared buffer, it gives back a response. with no data. If the remote PIM device wants to write data to the local PIM device, then the remote PIM device similarly initialize the remote to local request with data, and the local device gives a no data response. With such inter-device CXL communication protocols, here we can see how the collective communication primitives is realized. The peer-to-peer communication between CXL devices is accomplished by send and receive instructions. On top of this, we propose the multicast instruction and two new communication primitives, multicast and gather. In multicast, the source device sends data to destination devices, while in gather, the destination device receives data. The destination device receives data from all source devices sequentially. With these CXL communication primitives, we explored various parallel mapping strategies on the CENT architecture. In pipeline parallel mapping, the certain transformer blocks are mapped to a single CXL device. If there are like a large number of transformer blocks, they are allocated to multiple devices with, for example, 4 transformer blocks per device in this example. The inter-device communication only happens between 2 transformer blocks using the peer-to-peer communication primitive. Multiple prompts are executed in a pipeline manner. While in tensor parallel mapping, the transformer blocks within the single prompt are executed sequentially, and each of them is mapped across multiple CXL devices. Multicast and gather primitives are applied for these inter-device communications. Pipeline parallel mapping provides high serving throughput, while tensor parallel mapping prioritizes the latency. A hybrid approach of both pipeline and tensor parallel mappings can strike a balance between serving latency and throughput. Our evaluation methodology includes the performance, power, and cost model. The performance model starts from the workload mapper and trace generator. The PIM traces are fed into a remulator-based cycle accuracy simulator. The results are combined with an analytical model for CXL communication. The power model is based on the micron DRAM power model and synthesis results, while the cost model includes the PIM module cost, which is estimated as 10 times of the standard DRAM modules. And the custom design cost is estimated through NRE cost, that is non-recurrent cost. Non-recurrent cost means the labor cost, license cost, which is not related to the chip production volume, while the die and packaging cost is related to the production volume. Here is a detailed illustration of the performance model. On the left shows that the workload mapper actually parse the operators within each transformer block. For example, different large language models have different architectures. They utilize different operators. Like normalization can have some variants, some using standard layer normalizations like GPT, some using the RMS norm like Llama. Once decomposing the model architecture to operators, the trace generator try to decompose each operator, such as GenV, general purpose matrix vector operation, to the PIM IC, each of the PIM instruction, like in this example, write global buffer, write bias, macrobank, and read mac. These PIM instructions are further decomposed to the DRAM command in the AIM simulator. And this simulator is developed based on the emulator. Finally, the CXL communication latency is estimated through this analytical model. Then let's look at the micron DRAM power model. It starts from the IDD current. The IDD current is measured on the GDDR6 DRAMs and provided from the DRAM manufacturers. For example, it conducted a trace of gapless read and measure what is the IDD current need to be provided for this gapless read, or some other patterns of memory access. Based on the different memory traces provided, the measured IDD will be corresponding to different scenario. And using this current at different scenarios, we can calculate the power for different DRAM command or different scenario. For example, the background power means if there is no active read or write, what is the leakage current consumed by the power. So we can see the active background power and pre-charged background power in the first two formulas. Similarly, we can see how much power is consumed under the activation or pre-charge command, or the read or write command and refresh command. And then within the AIM simulator, we can see how many cycles is required corresponding to each of these commands. By combining the power and cycle numbers, we can calculate the energy consumption. And based on the energy consumption and cycle numbers, we can get the average power for the entire workload execution. For cost model, we use $10,000 per A100 GPU, which is half of the available retail prices obtained online. For PIM, we use 10 times the price of standard DRAM modules. For custom design cost, the left table chart shows the cost with different production volume. The green block shows the NRE cost, that is the non-recurrent cost. So we can see with higher production volume, the non-recurrent cost is amortized to a smaller number. And the decomposition of non-recurrent cost is shown on the right chart, including the system NRE packaging design, IP licensing, and labors, and the mask cost. We compare the CENT system versus the GPU baselines. CENT has 32 CXL devices having 512 GB of memory capacity, while the GPU baselines have 4 NVIDIA A100 GPUs with 320 GB of memory. CENT have around half of the peak compute throughput, that is T-flops, when compared to GPUs, but can provide 64 times higher peak memory bandwidth when compared to GPUs. CENT also have a lower total cost of ownership, that is 2.4 times lower using an owned TCU model, but it can provide even larger cost saving if we use a rental TCU model. The evaluation use 512 prefill tokens and 3.5K decoding tokens. CENT achieves an average of 2.3 times higher throughput when compared to the GPU baselines. Because CENT has a lower hardware cost, so it can finally generate more than 5 times more tokens per dollar when compared to GPUs as a more cost-effective solution. This chart compares the power consumption between Synth and GPUs. We can see in the 3 different model size, we use different number of Synth devices to make a power neutral comparison between Synth and GPU. The right chart shows the GPU power. So on the left chart, we can observe that the prefill and decoding stage on the GPU has a similar power consumption, which is conflicting with the observation that GPU is underutilized on the decoding phase. And the right figure can explain this gap. The right figure shows that there are 3 stages. The first stage is the initialization, where the GPU is idle. Nothing is running on the GPU. So we can see the blue line shows the frequency of the GPU. The A100 GPU has 2 types of the frequency. One is the base frequency, which is around the 1100 megahertz. Well, the boost frequency, that is the maximum frequency at 1400 megahertz. When the GPU is idle, it can easily run at the highest frequency, at the boost frequency. And the board power is around like 100 watts as an idle power. In the prefill stage, because the prefill stage is not memory bound and GPU can achieve the pretty good utilization. In this scenario, GPU board power can easily reach the TDP, that is 300 watts. Because the GPU power reaches the TDP, then it has to decrease its frequency from the boost frequency of 1400 megahertz to the 1100 or close to 1200. Because if the GPU maintains the boost frequency, its power can easily go much higher than TDP and resist the cooling problem. Well, on the decoding stage, we can see the GPU utilization decreases. However, its power is still close to the TDP. That is because GPU can raise its frequency and make it very close to the boost frequency. And that is the reason why in the prefill stage and decoding stage, GPU has similar power but different utilization. If the GPU improves its cooling technology, in the prefill stage, it can still raise its frequency, and then the power can reach around like 400 or even higher. Then let's look at some detailed analysis of the performance on Llama 70 model. This chart shows the Synth performance on long context. Synth outperforms GPU in the decoding stage, and this trend will be enhanced with the context length increasing, because GPUs can support less batch size at long context scenarios. Meanwhile, Synth also exhibits lower latency when compared to the GPU at the same throughput, so Synth can provide a better user experience. This chart shows the latency decomposition on Synth at different hardware components. We can see PIM latency dominates the entire latency. And these 6 scenarios, 6 rows shows different parallel mapping strategies. PP means pipeline parallel. TP means tensor parallel. With pipeline parallel, it actually serves multiple queries at the same time. It prioritizes the throughput, but increases the query latency for each of the requests. If we look at the last row, there is a single pipeline parallel stage. That is, only a single query is executed at this time. It has the lowest latency, but can have lower entire throughput when compared to the pipeline parallel as well. So we can see CXL communication, PNM accelerator, and host CPU does not conduct a large portion of latency when compared to the PIM modules. These two charts shows the scalability study on the performance at different number of devices. In our main evaluation, we choose 32 devices, which is marked at this red stars. But we can see with the device number increasing, the throughput can also increase almost linearly. The reason I say almost linearly is that from, for example, 40 to 42 devices, the throughput does not increase, but keep as a constant on the left figure. And on the right figure, it explains the reason, because with 40 devices, they can all be well utilized. But if we add one more device, when we pipeline 80 transformer blocks in the Llama 70B model, it can only utilize 40 devices efficiently. Therefore, the extra one or two device will not be well utilized, and that's why throughput is kept at 40 devices. But further, if we increase the device to a larger number, like 48, 56, or 80, then the performance, the entire throughput can further go up. The different colors in this chart shows a different data parallel. Data parallel means we store multiple model weight copies for each of the data parallel setup. To conclude, we observe that large language model inference serving on the GPU system requires large memory capacity, which limits the batch size. Further, the self-attention cannot even be batched. Both factors result in the low GPU utilization, which is caused by low operational intensity. To address this challenge, we use PIM to provide large internal bandwidth and propose the hierarchical PIM-PNM design to execute the entire transformer block on device and avoid any other execution on either CPU or GPU, providing a GPU-free solution, which is much more cost-effective than using the expensive GPU servers. To support the large memory capacity requirement, we use the scalable CXL interconnect and propose new inter-device communication primitives, which enables various parallel workload mapping options. The Sense system has lower hardware cost and better energy efficiency, finally achieving more than 5 times of tokens per dollar. Thank you all for listening and welcome for any questions. Here is the QR code for our paper and artifact of GitHub link.
All right. Thank you very much for your presentation. It was very interesting.
Yeah, so thank you for hosting.
I have a few questions. First of all, how do emerging model architectures are affected by this design? For example, mixture of experts where you activate part of all the weights in the fully connected layers. Do you need to perform any modifications to this architecture to better support the execution of such models?
Yeah, that is a good question. Mixture of expert is an emerging technology and has been well applied, widely applied in modern LLMs. So We actually studied the mixture of expert as well when like deploying it on the center architecture. So we can separate the mixture of expert architecture to self-attention and MOE, like the FFM part. So for self-attention, it does not affect much because it has the same behavior. And on the FFM part, we can distribute each of the expert across like multiple devices, just regard them as regard them as a standard FFM. And with the synth architecture, it can only support one queries within one pipeline stage because synth can only support vector matrix multiplication. If we have one queries serving at each moment, it will only activate like one or two expert among like 8 or 64 experts. So at the same time, we only load the FFM model weights from the specific DRAM rows for each of the device. That means we distribute each of the expert to all of the devices in this pipeline stage, and then execute each expert which is active sequentially. That if we activate two experts for one query, then we execute the vector matrix multiplication sequentially for these two experts. And that is the solution for MOE model mapping.
Thank you very much. Does anybody else want to ask any questions? If not, I can ask another one.
Yeah, of course.
Sure. I didn't see. Does this scheme require any particular quantization, or are you using general floating point arithmetic over here?
In the evaluation on synth, we don't apply any quantization and we use the standard BF16 format. Because we refer to the ISCC paper of the SK Hynix, the industrial protocol, and their design uses the BF16. So we just follow the same precision as that industry protocol prototype.
Yeah, I think also because you can support such large capacities, quantization is less important than in GPUs, where capacity is often the bottleneck for deploying larger models. So it makes sense to me.
Yeah, it's actually possible to further apply the quantization. So because the current nearbank processing unit uses the Mach reduction tree architecture, if we reduce the precision like from BF16 to FP8, integer 8 or integer 4, there may be a slight change of the nearbank processing unit is required like to make it compatible across like multiple like precision requirements. But theoretically, the entire architecture, like the interconnect and the PNM accelerators, can be still applicable to the different precision requirements.
Yeah. I think it could also potentially be faster with quantization, even faster, because you will not be as compute bound inside the PIM because you can do more with less in that case. If it's integer, for example.
Yeah, that is a good question. Let me think. So with quantization, indeed, we need less operations. And at the same time, we also reduce the amount of data need to be fetched from DRAM. So quantization does not affect the operational intensity because it reduces both the number of operations and the fetched data volume. So the quantization will indeed increase the throughput, but it will increase the throughput at both center and GPU. So the speed up is probably like a similar number, but I'm not sure. We can evaluate like see how does it scale.
Yeah, good. Very nice talk again. I'll ask for another round of questions if anyone's up for the taking.
There are actually 2 questions on YouTube, Andros. So I'm asking them very quickly. The first one is that, is the PNM device a custom designed by you, I think?
Yes, that is true. The PNM design is a custom design. The reason of this PNM design is that if we refer to the original industrial prototype of SK Hynix design, because the PIM module only supports the matrix vector multiplication or element-wise multiplication. The other operations, such as the normalization, the softmax, have to be conducted on CPU or either CPU or GPU. Then it requires the data movements between the PIM device and other like either host device or GPU to support the entire transformer block execution on the PIM device and provide a GPU-free solution. We designed this PNM unit to execute all of the operations other than vector matrix multiplication or the element-wise multiplication as shown in this figure. So we first look at what operations are required. Required means it is not efficient to be mapped to the PNM modules. After figuring out what operations is required, we design the PNM accelerators. If a custom accelerator is not enough, then we add a few RISC-V ports to make these PNM accelerators more flexible to support the future LLMs architectures.
Okay, yeah, I think that makes sense. The next question is also about what's the latency between inter-CXL communication and intra-CXL communication? I think he's asking about the difference between inter and intra-CXL communication latencies.
Okay, yeah, that's a good question. So let's first understand how the data are moved between these two scenarios. In this figure, we can first look at the intro device data flow, which is marked by the blue line. The intro device happens either between the shared buffer and the GDDR6 pin, or within the GDDR6 pin, like between the global buffer and DRAM bank. So the distance is shorter than inter-device communication because it happens within the PIM device. And the protocol it uses is the standard read or write. Standard read or write means the memory controller, or like here the PIM controller, conducts a standard read that is move the data from DRAM bank to this shared buffer. But it's slower, but the latency is lower than the normal CPU read, because here we don't need to read the data from the PIM device to the whole CPU, but to a like shared buffer locally on the device. So the latency is much lower than inter-device. Then let's look at how inter-device communication is conducted. It's shown by the black rows. So the inter-device communication happens reading a data from the shared buffer to the this is controlled by the inter-device communication controller. The data read from this shared buffer go through the CXL port and further to the CXL switch. The CXL switch figures out the destination device and received by the CXL port of the destination device and parsed to understand, okay, which memory address we need to store at the shared buffer. So this is basically going through the PCIe physical layer because the CXL communication is relying on the PCIe physical connection. I actually don't have the exact number, but we can roughly think of the inter-device communication as a communication through PCIe, which is much higher than on-device memory read.
Yeah, it makes sense. Yeah, thank you, Yufeng.
No problem. And thank you for all these good questions.
Right. Thanks, Yufeng, again for joining us.
Okay.
Yeah, and I think that's it.
Okay, yeah, thanks so much for the hosting from the Safari group. And it's a very nice journey.
Yeah, thank you so much, Yufeng. Great talk. And yeah, hope to see you soon. I don't know,
Yeah,
somewhere
hope to see you all.
in the conference. Yeah, take care.
Bye.